In this tutorial, we're going to be looking at taking derivatives using the chain rule. The chain rule is best thought of as something you apply when you have a composition of functions. That can be represented a number of ways. Traditional ways include if I express something as f of g of x. This is basically saying that I have two functions. I have one function which is f of x. I have another function which is g of x, and in this case the composition of functions says that the input of f is the output of g of x. So normally if we thought of this in terms of if we graphed y equals g of x, it's a pretty terrible looking g of x. If we graphed y equals g of x, then the input would be the x and the output would be the y. Then what we're basically saying is that this output, this y output, is going to become the input to f, and then of course f itself would have its own output. So when we have a composition of functions, we are chaining these things together. So when we take the derivatives, we also have to take into account that chaining effect. So if we were to write this a different way, we would write this as y equals f of g of x. So basically, the input to f, which is the contents of this square bracket, is the entire function g of x. And the rule we have for that, the chain rule itself, specifies that when you take the derivative of this, so if we take y prime, that is going to be equal to the derivative of the exterior function, which is f, and then we leave g of x intact, and then we multiply that whole thing by the derivative of the interior function, which would be g prime of x. So that's the standard definition for the chain rule. Now let's see that put into practice. So let's do an example. Pick a fairly simple example. And so in this case, I'm going to say let y be equal to, and I'm going to say it's going to be x squared plus 1 all to the power 5. So if we take a look, let's break this down into its two pieces. Inside this function, on the inside, I have x squared plus 1. And then that whole thing is being raised to the exponent 5. So I'm actually going to say, change my colors a little bit, I'm going to start off by saying that f of x, in this case, f of x is equal to something to the exponent 5. So x raised to the exponent 5. And then inside, that means that I have the function that's inside the brackets. That's another function that's going to be g of x is equal to x squared plus 1. And the chain rule lets us actually deal with these separately. So in this case, g of x, here is my g of x, and then I'm also going to need a g prime of x, and then I'm also going to need an f prime. So if this is f of x, then f prime of x is equal to 5x to the power 4. If I take the derivative of g prime of x, that is equal to simply 2x. So now that I know what f prime of x is and what g prime of x is, the way this is going to end up working itself out is I end up with y is equal to, so it's going to be f prime of g of x. So first of all, let's look at f prime. F prime is 5x to the power 4. So I'm going to write that as 5. Now, I would normally write this as x to the power 4. But it's not just x to the power 4. It's wherever I see an x here, I have to replace it with g of x. So instead of writing this as x to the power 4, I have to write this as bracket g of x to the power 4, which is x squared plus 1 all to the power 4. So here is f prime, 5 times this bracket to the power 4. That's my f prime. And then inside that bracket, I put my g of x. I put back the original function, which is right there. There's g of x. So that just goes right back into the same bracket. And then outside of the bracket, I take the derivative of g of x, which in this case was 2x. And to finish this question up, I would simplify. Constants, I've got 5 times 2, which is 10. I have an x, which I'll put in front instead of at the end. And then I'll write this as x squared plus 1 all to the power 4. And that is, sorry, the only thing I've made the mistake there is my notation, which is I have to put in my primes for taking the derivative. So in this case, the derivative is 10x, x squared plus 1 all to the power 4. So there's an example of using the chain rule. And the chain rule can be used in a number of circumstances that way. So let's do one more example, another relatively simple example using the chain rule. So that was example number 1. Let's look at example number 2. And I'll just make up another one. Now, I don't want you to get too hung up on what the labeling of these functions are. You can label them whatever you want, but for the case of, for this example, we're using this definition of the chain rule is defined by f prime of g of x times g prime of x. Now, there's an alternate way that we can look at the chain rule, and actually I think I'll explore that before I do this next example. So another way we can look at the chain rule is we can do what's known as a substitution. So if we have y equals f of g of x, then we're actually going to make a substitution, a change of variable. We're going to let u equal g of x. And if we let u equal g of x, then that means I can rewrite this as y equals f of u, which means the input to this function, the input to f is the actual change in variable, that's u. And so if we write the chain rule this way, then when I take my derivative, I end up with y equals f prime of u. That doesn't change anything, but I also have to take the derivative of the interior, which I write as du by dx, the derivative of u with respect to x. But if we look over here, du by dx, that is simply the derivative of this. Well, what is the derivative of g of x? That is equivalent to g prime of x. That means we're doing exactly the same thing. If you take a look, our substitution here, u is the same as g of x, so that goes in here. Du by dx is the same as g prime of x, so that goes here. So both of these definitions are both perfectly valid, and you should try out both of them to see which one you're most comfortable with. So let's do an example using that definition. Go to the next page. And so let's look at example number 2. And so with this one, how about I take y is equal to, and again, I'll do another polynomial, but this time I'll include a radical, which is really very similar. So I will put inside the bracket, I'm going to put the square root of x plus 1, and I'm going to raise all of this to the power 3. So again, now we could actually do this. We could expand this cubic out. So quite often you're presented with alternative methods for the chain rule, but that's not the point of what we're doing here. We just want to see how do we apply the chain rule. So in this case, I'm going to now you can see here there's no talk of functions. I don't have an f of x or a g of x. I just have this equation, y equals the square root of x plus 1 all cubed. So in this case, I'm going to make my change of variable. I'm going to let u equal the square root of x plus 1. And so if that's the case, I'm also going to need the derivative. Now to take the derivative of u, it's actually probably easier to put this into a power notation. So square root of x is the same as x to the 1/2 plus 1. and then the derivative of u with respect to x, basically saying the derivative of this thing, where x is the variable, which it obviously is going to be equal to 1/2 x to the negative 1/2, and then the derivative of the 1 is just a constant, so the derivative is 0. So now I have u, and I have du by dx, and so now I can make my change in variable here, which is this is the same as y equals u cubed, and so the derivative of this one, if I want y prime, now I'm actually going to write this using derivative notation, dy by dx, the derivative of y with respect to x is going to be equal to the derivative of this, which is 3u squared, but this is u. This is the derivative of y with respect to u, so we actually need to include du by dx. And so what is 3u squared? Well, we did a change of variable, so it turns out that u is equal to the square root of x plus 1, and that's all squared. And then du by dx, I'm putting at the end here, which is 1/2 x to the negative 1/2. And I could do some simplification here. The constants, 3 over 2, and then I have the square root of x plus 1, all squared in the numerator, and here I have an x to the negative 1/2, which is the same as the square root of x in the denominator. Now I'm not going to take this any further. We could rationalize that denominator if we wanted to, or if we were required to, but really what I want to focus on here is the taking of the derivative. So here I've taken the derivative, and that is my final result. So I think I'm going to leave that for now with this tutorial. I've done a couple of examples, a couple of fairly simple composite functions, and I've shown you two different ways that you can approach this. So good luck with taking those derivatives, and make sure you practice this. I'm also going to do a video tutorial on some more complicated composite functions that incorporate all of the derivative rules together.